All right, let's talk about something that honestly sounds like it's straight out of a sci-fi movie. We're talking about an AI that can literally read your code, just the raw source code, and tell you how fast it's going to run, how much memory it's going to eat up, all before you even compile it. Yeah, you heard that right. Just let that sink in for a second. One single model looks at your code and spits out memory usage, latency, even AI model accuracy, all without executing a single line. This isn't just a small step forward. This is a huge leap that could completely change the game for how we optimize software.
So the big question is, how on earth is that even possible? And to really get why this is such a breakthrough, you've got to understand why this has always been, well, a massive headache for developers.
Okay, so let's talk about the old way of doing things. For like decades, the tools we've had for this have been a total patchwork. A bunch of different custom-built things for very specific tasks. They were a nightmare to maintain and, honestly, super fragile.
And that brings us to the core shift here. We're moving from that messy world of bespoke, brittle tools to a whole new era with one single, unified model. And trust me, the difference is like night and day.
You see, the old way was just a constant uphill battle. You had to sit there and handcraft these super specific features for every single programming language and every single piece of hardware you were targeting. And the worst part? You change one tiny line of code and poof, the whole model could just break or become totally inaccurate. It was just slow, expensive, and a real pain. And this workflow, man, it just shows you how much manual work was involved. Every time you had a new task, a new update, you were basically starting over from square one. It was this endless cycle of repetitive work that just does not scale at all.
But now we have a totally new way of thinking. It's built on something called regression language models, or RLMs for short. Now, these are AI models that are usually amazing with text, right? But they've been cleverly adapted to predict numbers. And this is where things get really, really cool. So you remember that whole complicated multi-step pipeline we just talked about? Yeah, forget it. It gets replaced by this. It's so simple. You just feed your raw source code into this one unified model, and bam, out comes your performance metrics. That's it. It's that clean.
And the advantages here are just huge. We're talking about one model that's super versatile. It can predict memory, latency, even something as complex as model accuracy. It's robust because it's learning directly from the code, not some fragile features we cooked up. And maybe most importantly, it's fantastic at one key thing, ranking different code options to tell you which one is actually the best. Okay, so what's the secret? What's the magic trick that makes all this possible? Well, it's an idea that is so simple, it's brilliant. It all comes down to treating numbers as if they were just text. Basically, what the model is doing is called code-to-metric regression. Fancy term, but all it means is it reads code and spits out a number. Simple enough, right? But the real genius here isn't just that it can read the code. It's all about how it writes the answer. This is the big aha moment. See, language models are built to generate text, sequences of words. They're not really designed to just output a single raw number. So the researchers got clever and completely reframed the problem. So instead of forcing the model to spit out a number, like 12.58, they taught it to spell out the number, digit by digit, just like it would spell out a word. It predicts a sequence of text tokens, 1, then 2, then dot, then 5, then 8. And that one simple trick, it unlocks everything. So why is that so unbelievably powerful? Well, because it completely gets around the huge problem of dealing with different units and scales. The model doesn't have to worry if it's predicting memory in megabytes, latency in milliseconds, or accuracy as a percentage. To the model, it's all just a sequence of characters to spell out. This lets it learn the trade-offs between all these different metrics totally seamlessly.
All right, that all sounds amazing in theory, right? But the real question is, does it actually work? Let's dive into the results and see how this thing performs in the real world.
Now, before we jump into the raw numbers, let's talk about what actually matters when you're in the trenches, writing code. Most of the time, you don't need the exact performance value down to the last decimal point. What you really need to know is, out of these few options I've written, which one is the best? It's all about getting the ranking right. And here it is, the headline result. The model hit a Spearman rank correlation of over 0.9. Now, that's a fancy sounding stat, but all it means is how well the model's ranking of code solutions matches the actual true ranking. A perfect score is 1.0. So getting above a 0.9, yeah, that's insanely good. It means the model is exceptional at telling you which code is the winner.
And it gets better. This isn't just for one language. This amazing performance holds up across a whole bunch of them. We're seeing great results for C++, Python, Java, and this is all from that same single model. It was trained on a dataset called CodeNet that has 17 different languages. It's just incredibly versatile. And we're not just talking about simple scripts either. This thing was tested in the super complex world of neural architecture search, that's NAS for short, which is basically using AI to design other AIs. And it totally held its own. It hit a solid Kendall-Tau score, which is another one of those ranking metrics, and the really killer feature, it could predict how an architecture would perform on totally different hardware, which has always been a ridiculously hard problem to solve. So let's pull back for a second. What does all of this mean for the future of how we build software? Because this isn't just some cool research paper. This has some really big practical implications for all of us. So what's under the hood? It's a pretty compact model, actually, around 300 million parameters. And it's built on a solid foundation. It was initialized from T5 Gemma. What that means is it didn't start from scratch. It already had a deep pre-trained understanding of both natural language and code, which gave it a huge leg up. And that brings us to the big finale, the really crucial point. Just imagine for a second, what if this was built right into our daily workflow? Imagine every single pull request you make gets automatically analyzed. It flags any performance regressions before it gets merged. We're not just talking about making code a little bit faster, we're talking about a fundamentally smarter, more efficient, and way more reliable way to build software. The potential here is absolutely transformative.